our last talk in the morning, we have Liviu Păunescu from the Romanian Academy to tell us about finite von Neumann algebras, soficity, and solidity.
Thank you for the introduction, and I want to thank the organizers for inviting me to this nice conference. So the setting of my talk is finite von Neumann algebras. These are some specific star unital subalgebras in bounded operators on Hilbert space. What will be highly important for us today is that we work only with those that have a trace, a linear functional. Trace of the identity is 1, and we have the trace equation. Trace of xy is equal to trace of yx. So of course I'm skipping a lot of details here. Let's just quickly see some basic examples. The model to have in mind is matrix algebras. So Mn of C, where the trace of a matrix, I'll denote by capital letters matrices. So the trace of a matrix is the average of the entries on the diagonal. I need the trace of the identity to be 1. Okay, the second example that we'll work with is probability spaces. So if you take a probability space, you have an abelian von Neumann algebra where the trace of a function is just the integral. And kind of you already see the beauty of the theory, because under the same set of axioms that I didn't write, you have matrix algebras and probability spaces. So this is why sometimes we call the trace a non-commutative integral. So at least for today's talks, I want you to give the trace the same privileges that you give to an integral. Okay? The first kind of non-trivial example is group algebra, the familiar group algebra. So elements in a group algebra are just linearization of the group. So sum of some unitaries indexed by elements of the group multiplied with some scalars. So this UG, they just encode the group structure. UG is UGH, and UG star is UG minus 1. Okay. The next example, let me use another blackboard. So the next example is a combination of the last two. For this one, you need a group action, and you construct the cross product. So elements here are same type of sums, just that now the difference is that instead of multiplying only with scalars, you multiply with functions in this abelian subalgebra. Okay, when you have the trace equation, UG, I'll need some more space, UGF, UG star is equal to alpha G of F. So when you work with cross product, there are 3 things to keep in mind. First of all, they contain an abelian subalgebra. Second one, they contain a copy of the group algebra. So all those equations that I wrote here, they are also valid in a cross product. And the cross product equation that will tell you that the unitaries corresponding to group elements act on the abelian subalgebra in the way prescribed by their action. This is what I'm writing here. And I forgot to tell you what is the trace. So the trace of an element in a group algebra is just the coefficient of the identity. And the trace of an element in a cross product is a combination of the 2 traces, so the integral of the functions corresponding to the identity. And the last example that we'll work with today, so the observation is that this algebra actually does not depend on the action, but only on the orbit equivalence of that action. So if you start with an equivalence relation in X, then you construct what is called the Feldman-Moore construction, that are just matrices. Again, matrices, so functions from E to complex numbers that you treat them as matrices. So if you want to multiply to such objects, then it's the familiar formula AXZ BZY. And the trace of such an object is just the integral on the diagonal. X, integral over x. Okay. So it is a nice picture because it's circular, it starts with matrices, it ends up with matrices, and it's passing by groups and group actions. Okay. So there are several questions, several basic questions that you can ask in this setting. The one that we'll study today is cone embedding problem that we kind of now know it's false, but there is still the question, which of these examples that I wrote on the blackboard are approximable by matrices? So which von Neumann algebras are locally approximable by matrices with respect to the trace. Again, I'm leaving a lot of details out. We'll study this question for this list of examples. If you never saw cone embedding before, just think of the picture of the Lebesgue integral, of the definition of Lebesgue integral. So you take a measurable function and you approximate it with simple functions, functions that have only a finite number of values. So cone embedding problem is a non-commutative equivalent of this picture, the same way that the trace is a non-commutative integral. Okay, so matrix algebras are always approximable by matrices. There is nothing to be said here. Abelian von Neumann algebras are always approximable, and the proof is not much more than the theorem that I just stated, that simple functions are dense in L infinity of x, and simple functions can be modeled by basically diagonal matrices. Okay, so the first non-trivial example to discuss is when is a group algebra approximable, cone approximable in this way, and this is the notion of hyperlinear group that I will write the definition, but I will split the definition into 4 parts because I will need it for the rest of my talk. So from now on, we'll work with this object with a sequence of maps. So phi, it will be a sequence of maps from the group G into unitary matrices in some dimension. So fix nk, a sequence of natural numbers going to infinity, and we will work with this object. Maps, a sequence of maps from the group G to unitary matrices. If I will refer to such a collection by morphism, by this I will mean that each of these maps should be a morphism. So it will be just a sequence of representation. The second definition is a weaker version of this, and it's the important one, the notion of hyperlinear morphism. So now I'm taking only a sequence of maps, but I ask them in the limit to be homomorphism. So I'm asking that the limit in K of the Hilbert-Schmidt distance between Pk of J, Pk of H, and Pk GH, I want this to go to 0 for each G and H in the group. So I have to tell you what is the Hilbert-Schmidt distance. It comes from the Hilbert-Schmidt norm. That is just the trace norm. So square root of trace of K star A. And if you do the computation, you'll see that it's a norm 2. So 1 over A, sum of all the entries of A squared. Okay. So I'm asking this limit to be 0 for each 2 elements, but the speed of convergence can be different if you vary the elements in your group. So this fact, this observation corresponds to the word locally here. Okay. Each group will have a hyperlinear morphism because you can send everything to identity. And the group is hyperlinear if it has a non-trivial hyperlinear morphism. So how do I say non-trivial? There are many ways to say it, but I will introduce another object that I will need for the rest of my talk, the trace of a morphism. So if you have a hyperlinear morphism, you just construct a function from the group G to complex numbers. Trace of G evaluated in a point H is just limit of trace of phi k j. Okay. And of course you can complain that maybe this limit does not exist always. There are two ways to correct this. You either restrict yourself to only hyperlinear morphism for which this limit always exists. There is no loss in generality if you do that. Or more elegantly, use an ultrafilter and you notice that this is a bounded sequence because it's trace of a unitary. So the limit will always exist. And the definition that I wanted to write, a group is hyperlinear if it has a hyperlinear morphism that is trace preserving, such that trace phi of each non-trivial element is 0. So why I'm calling this property trace preserving? Because if you look at the trace on the group algebra, you'll notice that the trace of each unitary UG corresponding to a group element is 0 if G is different than identity. So yeah, we know that cone-embedding problem is false, but we still don't have an example of a non-hyperlinear group, meaning we don't know if one of the counterexamples to this question is of this type. Okay. So what about cross products? When can they be approximable, cone-approximable using matrices? So as I said, there are three things that you have to ensure. You first want to approximate L infinity of x using matrices, that you can always do. You want to approximate your group using matrices. So in order for a cross product to be approximable, you need the group to be hyperlinear. No surprise there. But then you have to ensure this equation. Yeah? Matrices approximating group elements should act on matrices approximating elements in the abelian subalgebra in the way prescribed by the action. And I don't think that you can really study it in this direction. And it's very tempting to think of this picture of permutation matrices that act on diagonal matrices. So these are matrices that have only one entry of 1 on each row on each column. It's a subgroup isomorphic to the symmetric group. And these are matrices having only diagonal entries. So if you take a permutation and the diagonal matrix, then you can construct this matrix that it is basically the same matrix as A with the entries permuted according to what B is saying. Okay. So yeah, I cannot stress enough how important this picture, as basic as it is, how important this picture is to my work. So it's tempting to say, let's use only diagonal matrices to approximate L infinity of x. We can do that. Let's use only permutation matrices when we approximate G. And then at least now, instead of ensuring the equality of two matrices, at least we have two diagonal matrices. And it's much easier to ensure this type of equality. So it appears the question, if we have a hyperlinear group, meaning that it can be approximated this way using unitary matrices, can we approximate it using only permutation matrices? And this is open, this is the notion of soficity. Okay? So basically all those definitions, I have to rewrite them in the context of permutations. So by a sophic morphism, I will mean a collection of maps from the group G to permutation matrices with the same requirement, this requirement. Okay? In the same way, you can define the trace of a Sophic morphism. That the difference is that now you can interpret the trace as the number of fixed points of those permutations, because that is the trace of a permutation matrix. And the group is Sophic if it has a trace-preserving Sophic morphism. Okay. And one last definition before proceeding to some questions and results. It's a familiar definition. It's the notion of residue finite, but I'll write it differently. So G is residue finite if there exists a morphism into permutations. So this is a morphism, P and K here. Okay. Trace preserving. So trace of trace phi of G is equal to 0 for each non-trivial G. Of course, it's an unorthodox way of writing residue finiteness, but it's easy to see that it's equivalent to the usual definition, and it incorporates well with my other definition of Sophic and hyperlinear group. Okay, so now it's a good moment to ask this question by Gulnara. All hyperbolic groups are residue finite if and only if all hyperbolic groups are Sophic. So why would we care about hyperbolicity of about sophicity of hyperbolic groups? Well, free groups are Sophic, they are reasonably finite, but more than that, triple objects like triple groups or triple equivalence relations are Sophic. I didn't write what it means for an equivalence relation to be Sophic, but the ingredients are on the blackboard. So what I want to say is that it's easy to use triability to prove sophicity. And sophicity is in a way a generalization of residue finiteness having a metric flavor to it. It's a metric approximation property. So if you look at hyperbolic groups that kind of have a similar geometry, not necessarily, but close by geometry as free groups, you'd expect us to be able to prove that they are Sophic. But we are not, and according to this conjecture, it might be actually as difficult as proving that they are residue finite. Okay. And now it's a good moment for me to introduce the notion of stability that can be viewed as a possible way to upgrade sophicity to residue finiteness. So I will again split this definition into two parts. If E and C are hyperbolic morphisms, hyperlinear morphism. We'll call that they are equivalent if limit of the Hilbert-Schmidt distance between phi k and j and ck of j is equal to 0. So in the limit, it's basically the same matrices that you are using. And again, I'm allowing the speed of convergence to vary if you vary the element in the group. Okay. And a group is called, if I did it with Sophic, okay. So G is called stable in permutation. If any Sophic morphism is equivalent to a morphism permutation. There exists phi psi morphism in permutation such that phi is equivalent to psi. Okay. So each sequence of almost homomorphisms can be corrected to a sequence of exact morphisms. Yeah. And the original motivation is this proposition by Glebsky in the context of equations, and for groups it's a joint with Dolnara. G sophic and P stable, then G is raised to infinite. So with the definitions, it's quite easy to see this statement. So if G is sophic, then it has a trace-preserving sophic morphism. If it is P stable, then you can correct that morphism, that sophic morphism, to a morphism in permutation. It will have to be trace-preserving, and that is the definition of residually finiteness. So of course I didn't write the observation, but it's an easy observation that if you have two equivalent morphisms, take your favorite flavor of morphisms, then they have the same trace. Okay. That will be important later. Now the discussion about stability is going to amenability, because in the context of finite von Neumann algebras, we have a very good understanding of amenability, and these notions of Sophic groups and stability benefit from this knowledge. But that is a longer discussion, and before that I want to, in order to better sell the notion of stability to this audience, I want to write this result by Lazarovich, Lewitt, and Minsk. Surface groups are flexible stable. Is stable. So what does it mean for a group to be flexible stable? Well, basically the same thing. The difference is that you allow your morphism in permutation to, you're allowed to add some points to these permutations in case you need it. So the notion appeared in an article by Becker and Botsky. Sophic property T groups are not stable. So how do they prove this? Infinite. So you take a morphism into permutation, okay, a sequence of maps. A morphism from G to permutation matrices is the same thing as an action of G on a set of n elements. This will become important later in my talk. So take out one of these n elements, so you remain with only n minus 1 points, and everything that comes from this action and can be projected here, you project. So you get a map, and this time it's just a map, not a morphism, from G to P minus 1, Pn minus 1. So this will be an almost morphism. If you take a sequence of this, you will get a Sophic morphism, because in the limit the error that comes from removing one point becomes smaller and smaller. And you use property T to show that if you want to correct this sequence of almost morphisms to a morphism, the only way to do it is to add your point back. Okay. So property T groups are not P stable. They might be flexible stable when you are allowed to add points back. And about surface groups, we know that they have this type of stability. We don't know about usual stability or not.
Is flexibly stable enough to cover your suffix implies residually finite implication?
Yes. Yeah, and the group is geometric. Okay, so it's using hyperbolic surfaces. So you can use negative curvature techniques to get results about stability. Okay, now let's talk about amenability. So there are a series of 3 results. A joint work with Gulnara. Abelian groups. Are p-stable. Then there exists a result by Hadwin and Schulman. For amenable groups, to G amenable, G is Hilbert-Schmidt stable. So many of my definitions today come in 2 flavors, one for hyperlinearity and one for soficity, meaning one in unitaries and one in permutations. So I didn't write what Hilbert-Schmidt stable is, but it's exactly the same definition as, where did I write here? As p-stability, the only difference is that you use hyperlinear morphisms and you want them to be close to a usual morphism in unitaries. It's the same flavor of notion. So G is Hilbert-Schmidt stable if and only if any character is residually finite. And the third result is due to Becker.
What is a character? What is residually finite?
I will say later, okay. I agree that there are some definitions missing. For now on, I just want to present the idea that we have complete characterization of stability for Hilbert-Schmidt and for permutation stability in the case of amenable groups. We'll talk later more about these notions. So Berger, Lubowski, Tom. Again, G amenable. G is p-stable if and only if any invariant random subgroup is cosophic in G. So the way I see these 2 definitions, we'll talk more about this. They are generalization of residually finiteness. They are residually finiteness on steroids in a way. So how do you prove these theorems? Well, it's by the means of conjugacy. So for 2 morphisms, hyperlinear or sophic morphisms, we call them conjugated if there exists a sequence of unitary matrices such that U, phi, U star is equivalent to psi. So when you take the matrices that phi uses and you conjugate them with these unitary matrices, you get something equivalent to psi. Okay, and this notion is important because amenability will give you plenty of examples where these relations hold. So first theorem that I want to write in this respect, it's kind of common knowledge. It was difficult for us to attribute this result. We find it something in an article by Hadwin and Shen. So if G amenable is amenable, then phi and c are conjugated if and only if they have the same trace. Trace of phi is equal to trace of c. So I'm referring to two hyperlinear morphisms. So of course that if two hyperlinear morphisms are conjugated, then they must have the same trace. So this direction is trivial, because this operation, conjugacy, preserves the trace, and as I said, for two equivalent hyperbolic morphisms, you have the same trace. So what this theorem is saying is that for amenable groups, and it's important for a group to be amenable, you also have the reverse. Having the same trace is enough to guarantee conjugacy. And now I kind of have a hint of what this statement is saying. Is saying for each possible trace that you get when you use a hyperlinear morphism, then you realize it using a sequence of a morphism, not a hyperlinear morphism. Okay, and being conjugated would be enough to deduce Hilbert instability. So what about sophic morphisms? So those are hyperlinear, and I'm referring to. It's not equivalent here, it's conjugacy. So phi, c are conjugated. If and only if they have the same trace, not equivalent. So now we are asking the same question, what about sophic morphisms? And when then to be conjugated by a permutation, by a sequence of permutation, not by a sequence of unitary matrices, as is usually the case with soficity. So there is this classic result by Elek and Szabo. Again, G amenable. And you take two trace-preserving sophic morphisms. So phi and c are sophic morphisms such that trace phi of g is equal to 0 is equal to trace c of g for each non-trivial g. Then the conclusion is that phi and c are, and I will say p conjugated. Meaning that they are conjugated by a sequence of permutation matrices instead of unitaries. And this is the result that we used to prove this theorem, and this kind of maximum that you can get out of the classic Elek-Szabo, because you work with all sophic morphisms and you want them to reduce only to trace-preserving sophic morphisms. And you kind of need abelianity to be able to do that. So what about general sophic morphisms? Can we hope a result like this, that only having the same trace is enough to guarantee a sequence of permutations? And the answer is no. And I will give you an example. So the example is quite easy to construct. It's of this group Z2 times Z2 into permutations of dimension 6. So I will write some permutations now. Phi1 of A, I'm denoting by A, B, and C the non-trivial elements of this group. Phi1 of A, it will be a permutation composed of two cycles of length 2 and two fixed points. The same one will be Phi2 of A. So 1, 2 is a cycle, 3, 4, and 5 and 6 are fixed points. Phi1 of B will be of the same cycle structure, but now I'm using 1, 3 as a cycle and 2, 4. Again, 5, 6 are fixed points. And Phi2 of B, I'm keeping 1, 2 as a cycle, and I'm using 3, 4 as fixed points. And now I'm making 5, 6 a cycle. And Phi1 of C has to be the product of these two permutations. If you do the computation, you'll see that it is 1, 4, 2, 3, and 5, 6 are fixed points. And the same thing here. The product, which will be 1 and 2 fixed points, 3, 4 cycle, and same 5, 6. So if you look here, you'll see that the trace of all... One moment. Is 1/3. So the trace of all the permutations that I wrote on the blackboard is 1/3. The difference is that the first collection has 2 common fixed points, while the second collection don't have any fixed points. So you can clearly see that there cannot be a permutation that will simultaneously conjugate the first family into the second family. But that theorem, Hadwin and Shen, is still valid, so you'll find a unitary matrix that will conjugate these 3 permutations into these 3 permutations.
I mean, P6 is famously special, right? It kind of smells slightly like maybe you twisted with this exceptional automorphism or something. I'm sure that's not true, but could you reassure us that that's...
Yes, it's not true. Yes. You can come up with larger examples, and I actually need, anyway, a sequence of these maps to yeah, I know that P6 is special, but it's not that because of that. Yeah, so what I want to say is that even though these 3 permutations here don't have common fixed points, they have common eigenvectors. So that unitary will send these 5 and 6 to those 2 common eigenvectors. This is why it exists. But hopefully this example, it's enough motivation to introduce this object that we call action trace. So you have an action, and that is the difference, the main difference between hyperlinearity and soficity. When you have soficity, it's always an action of the group somewhere. So if you have an action, we define an A is a finite subset of the group G. We define what we call action trace of alpha, just the measure of the set of common fixed points. So measure the set X with the property that alpha G of X is equal to X for each G in A. And for a Sophic morphism, and I need it to be Sophic morphism, the action trace of P, it will be limit in K, 1/nk, the cardinality of the common fixed points. So I, with the property that phi k of J applied to I is I. So phi k of J is a permutation. So this is for each G in G. So those action traces are now functions from the finite subset of G to basically 0, 1. It is hard for me to convince you in this language that these 2 are the same definition. Thanks. So these are the same definition because, as I said, when you have a Sophic morphism, you actually have an action of the group G on what is called the upspace, but for that I really need ultra products. Let me now write the theorem. So if there is a kind of statement that can be used by Neumann and Schauer, but in this setting is due to Becker, Rubowski, and Tom. So G amenable PMC Sophic morphisms then PMC are conjugated, are P conjugated by a permutation if and only if the action trace is the same. So again, in this direction, it's trivial to see if they are conjugated by a permutation, then this invariant must be kept, and the theorem is that in case of amenable groups, it's the same. And actually, this is the action trace is not a new object these are invariant random subgroups in disguise. So the definition of invariant random subgroup, IRS is a measure, a G-invariant measure on the space of subgroups of G that you view as a topological subspace in 0, 1 G. So yeah, I don't want to insist too much how much time I have left. This is a generalization of the notion of normal subgroups. If you don't have enough normal subgroups, you can look at invariant random subgroups, maybe to solve your problem. What I hope that I managed to do in this talk is to present them as so apart from them being a generalization of normal subgroups, I wanted to present them as a generalized non-commutative integral. Yeah. So we started with the trace that, as I said, is a generalized, is a non-commutative integral, and this in a way is a generalized trace. Okay. So this part. What else can we do with these theorems? The discussion is about amalgamated products. I know that for this audience it will be very interesting, amalgamated products over free groups. And also for us it will be a huge breakthrough if we can say something about soficity or stability in the case of amalgamated products over free groups. But we can actually say only something in case of amenability because we have these theorems. But before that, let me tell you another result. So these characterizations are not just some nice mathematics. We can really use them to get examples of stable groups. So theorem again, Becker-Rubot-Canton. If G is amenable, countable subgroups on each almost invariant, almost normal subgroup is profinitely closed. So only this thing, countable subgroups, countable number of subgroups, and this property of almost normal subgroups is enough to deduce that each invariant random subgroup is cosophic. So if in addition you know that you are amenable, then G is stable in permutation. And example, BS1n, Banzak solitaire of 1n. You can apply this. So what about amalgamated products that I promised? First of all, an order result. So if G1, G2 are hyperlinear or sophic, and H is amenable, then we know that the amalgamated product is hyperlinear, sophic. So this is an older result, 2010-2011. Now, if you want to prove hyperlinear stability or p-stability for an amalgamated product, you can assume that G1 is p-stable, very reasonable assumption. So you take a sophic morphism and you correct it to a sequence of morphisms on G1. But then when you use the p stability of G2, you want to correct your morphisms, but they are already prescribed on this subgroup by what you used on this part of the group. So this gave rise to this notion of constraint stable. The definition, I'm taking a pair of groups, so H a subgroup in G, and I'm taking a morphism into permutations, Pk from H to P and K. So this is morphisms. And I will say that G is phi constraint P stable if for each sophic morphisms that restricted to the subgroup H is equivalent P, there exists theta, a morphism in permutation from G to P and K, morphism such that theta is equivalent to psi and theta restricted to H is phi. So here we have equality, not only equivalence. So if you compare this definition to the definition of stability, I have it somewhere on the blackboard. Anyway, you'll see that it's the same thing. So for each sophic morphism, you want to find a morphism that is equivalent to the original one. The difference is that now you ask that on a subgroup, you have your permutations prescribed. You are obliged to use those permutations. And let me write with the theorem that will justify this notion. Joint work. If G1 is P stable and G2 is P constraint P stable for each morphism in H of H morphism, then the amalgamated product is P stable. And I forgot to write the most important part. Unfortunately, we need H finite. It appears in too many parts of the proof, and it's possible that for this type of result where you only ask the stability of G1 and nothing else, no other condition on G1, probably you can get results only for finite. So once you understand the notion of constraint stability, this is not that much of a theorem. The difficulty consists in finding examples, finding groups for which this can be applied. So one possible example is again G is stable. Then this type of group G amalgamated over H BS1 and cross product H is P stable. You can replace BS1N with any other group that satisfies the condition of this theorem. And there are also some other generalization, not necessarily a cross product here, but I don't want to give you some extra definitions, and I only have 10 seconds left. So.
Questions?
I just want to make sure I've understood the Becker-Lobotski-Tom theorem on the right here. So, first, so action trace coming from a sophic morphism, that's coming from the probability action associated with the limiting IRS of the sophic morphism. Is that what's implicit in action trace?
So we can just use this definition because those are permutations.
Sure.
E is an element in the set 1 and K.
I guess I'm checking why that definition is equivalent to the one above.
To the one above.
To the one above.
Because when you have a sophic morphism, you have an action of the group onto the log space. Are you familiar with cross products, with ultra products?
I'm not familiar with the Loeb space, but I suppose I'm asking if that's the same thing as the limiting IRS association.
IRS is a completely different viewpoint. I don't know if...
It's the same.
It is the same, thank you. And then you can recover the probability action from the action trace. That's the point.
The probability...
First definition of action trace again, given the action trace you can find X. Is that correct?
No, you get the IRS, but the IRS that is not enough.
Sorry, you can recover the IRS. Beg your pardon.
You have lots of different reactions that have the same trivial IRS, but they are different.
Okay.
Any other questions? And I guess I wanted to ask, perhaps that was a bit, how plausible do you believe that surface groups should be actually stable or not?
That's a good question, because the proof is kind of geometric, and where is Nir? Do we have Nir? Maybe he's a better...
Oh, yeah, maybe. Yeah, maybe. I mean, so
I think there was an obstruction, a geometric obstruction of area or something.
I mean, it's hard to tell from, like, the proof, I don't think the proof will give you.
Well, I mean, I suppose I'm asking because somehow, of course, as soon as you start talking about analyzing products, if you wanted to go beyond H-band finite, somehow that's the easiest example. Seems like a big...
Yeah, my guess is that if you want to go beyond the H finite, you really will have to have some conditions also on the other part.
Right.
I mean, you'll have to be, at least you'll have to be careful on how you choose your...
Yeah, but I mean, in the case of a surface group, it's a very specific H, right? It's one particular Z in the free group, it's a very specific. So. Any other questions? Okay, if not, let's thank you again, and also always